When I started creating videos, I assumed the Sine function was the perfect function for animating motion. Granted, it makes for very smooth visuals. I use it for horizontal and vertical shifting, zooming in and out, and fading an object by toggling its opacity. But it wasn't long before I started running into its limitations. For example, zooming in visually appeared to start fast and end slow. Zooming out had the opposite effect. If I wanted to move the edge of the shape to the center and zoom in, but at the same time, the point of reference would be pushed out of view and then unnaturally returned to the center. I have since discovered that exponential functions are better for zooming, but we're going to talk about something else. Right now, I want to teach you how to control velocity at a key frame, something that is very annoying to do with Sine. These points represent the horizontal position of an object at 3 key frames. Connecting them with sinusoidal curves produces this motion. Now, there's nothing wrong with the motion, but it forces a velocity of 0, meaning the rocket will come to a complete stop at each key frame. To change this, we should switch functions. These curves may not yet look it, but they are cubic. Cubics give us direct control over the rocket's velocity at each key frame. The curves will bend to the will of the desired velocity. We'll start it at 0, which gives us motion that is nearly identical to before, but now we have the power to explore. We can make the velocity positive. We can make it negative, which causes the rocket to travel backward. We can even control the incoming and outgoing velocities independently. We can also change the velocities at the very beginning and end. With the sinusoidal curves, we had control over boundary position, but with the cubic curves, we can also control boundary velocity. Stick around and I will teach you how to control boundary conditions of animations with both sinusoidal and cubic functions in Desmos. Earlier, I said that I wanted to teach you how to control an object's velocity through a key frame. I'm going to do more than that. I actually want to walk through how we can control an object's initial and final positions and velocities over an animated segment. Now, I also hinted that this is annoying to do with a sinusoidal function, but it's not impossible. And you will soon be convinced that it's better we do this with a cubic function, but I still wanted to show you how this can be done with a sinusoidal function. So Sine's got 4 parameters we can work with, A, B, C, and D. However, unfortunately, none of these is directly connected to any of the boundary conditions that we're trying to set. That is, D itself is not the final position, B itself is not the initial velocity, or any of those things. They're connected, but we're not going to be able to solve for all of them explicitly. But anyways, A is the amplitude, B is connected to the period, C is the horizontal or phase shift, and D is the vertical shift. We're going to need the derivative function because we're working with velocities. Our variable t here for time is going to vary from 0 to capital T, where capital T is the length of the animation. That could be whatever you want, 2 seconds, 5 seconds, 20 seconds. So f of 0 is your initial position, f of capital T is your final position, and then of course your initial and final velocity. So the way that this is going to work, and forgive me if I misrepresent this as I'm still trying to wrap my mind around it, but I believe all you can do here is pick 3 of the 4 and the nature of the function will set the 4th automatically. That is, we can choose both positions and 1 velocity or both velocities and 1 position, but we cannot determine all 4. Okay, here comes the math. If we plug 0 into the function, we get an expression for our initial position, which again, note that it depends upon all 4 parameters. That's why this gets a little frustrating. Same thing for final position, and then we can plug in 0 and capital T into the derivative to get expressions for our initial and final velocities. At least the velocities only depend upon 3 of the 4 parameters. So if we subtract the initial position from the final position, we can at least eliminate D. We can solve the initial velocity for C. It has inverse cosine, but better than nothing. And then if we compose those, we get an expression for the difference in the positions that only depends upon A and B. Now, unfortunately, we can't explicitly solve this for A or B, but hey, at least we're down to 2 parameters. So here's what we're going to do. We're going to head over to Desmos in a minute and set our desired values for the initial position, the final position, the initial velocity, and our animation run time. We will then guess an amplitude that we think will work for those desired boundary conditions. Now, we'll probably be wrong. There will probably be some trial and error. And then what I'm calling step 3 here is, since we can't solve for B explicitly, we're going to take the expression above, replace B with X's, all the B's with X's, and treat it as a function in X. We're going to graph that in Desmos, see where it intersects the difference in positions, and just manually type that in. We're going to let the computer give us a value. It will be rounded, but again, we don't have a choice because we can't actually solve for it. And then C will automatically be calculated from the initial velocity expression, and D will automatically be calculated from the initial position expression. But anyways, let's head over to Desmos. There is a link in the description to this Desmos file if you would like to play around with it yourself. But let's go through what I said we were going to do. So first steps, I said I'm going to set my initial and final positions, my initial velocity, and my animation runtime. So I've got those at 6, 10, 2, and 2. And then let's go over here. And I said, okay, we're going to guess a value for our amplitude. So here, I'm going to start with 2. I'm going to see would an amplitude of 2 connect these 2 segments with the boundary conditions that I'm asking for over 2 seconds. Notice the gap between them is 2. That's your 2 seconds right there. So that's where I'm going to go down here. And this is that big step 3 function that I typed out. And I'm going to look here and I'm going to see, does this function intersect? Notice I've graphed the difference in our positions, desired positions. Do these intersect? And they don't. We have a little gap between them. So that means that an amplitude of 2 will not work. So let me bump this up to 2.2. And there we go. Now we have some intersection. So we're going to look here and we're saying, okay, the computer says that this works when B is 4.32015. So I'm going to manually type that in for B. Now it is rounded to 5 decimal places, but let's see, 32015, 32015. And if we go up here, we'll see, oh, look at that. We do have a sinusoidal curve that is connecting our 2 segments with the desired boundary conditions. Now I want to check those. My initial position is 6 as desired. My final position is 9.9999. So functionally 10. And again, that is rounded because the computer returns a rounded value, right? That 4.32015, that was rounded. Our initial velocity is 2 as desired. And this is the part that we're not controlling. We have no control over this. The final position, or sorry, the final velocity is 5.15-ish. So there it is. I mean, it worked. I mean, that is some type of success right there. Now, we've been talking about animation. What are we animating? Well, here's our animated particle. So if I hit play, this particle is going to start with a velocity of 2, and it's going to start at 6, and it's going to end at 10. So let's see. Here we go. Play. So it does successfully do those things. We have achieved our desired boundary conditions, but what do we not like about this? Well, it oscillates. It doesn't directly go from 6 to 10. It actually overshoots 10, comes back, and then returns. So this is behavior that I don't want. I want direct travel from the initial position to the final position. So what I might do is like, well, let's pick a different value for B. How about this one out here? 8.09847, 09847. And there we go. We get another curve that satisfies our boundary conditions. But what did we end up with? More oscillations. So here's what that animation will look like. not exactly what I'm after here, right? I want direct travel. So maybe an amplitude of 2.2 was not the best. Let me bump this all the way up to 3. And you notice now is that we're going to get this intersection right here, an intersection that we did not have before. It's the intersection that's closest to the origin, the smallest possible positive value for B, 0.7608. 0.7608. And there we go. Now we have a connection here without oscillation. A direct path from 6 to 10 over 2 seconds. And again, let's check. Our initial position is 6. Our final position is basically 10. Our initial velocity is still 2. And this ends up making our final velocity approximately 1.2. So if we go here and we hit that play button, we're going to see direct travel from 6 to 10. No oscillation, no overshooting. It basically looks linear, but this little segment here is that of a sinusoidal curve. So it's possible, it's possible to get 3 of the 4 desired boundary conditions. Now you can mess around with this and get really close to having, a final velocity of what you want it to be, but it's a lot of trial and error, a lot of playing, a lot of fighting, stuff that is very easily resolved when we use cubic instead of sinusoidal. And that is what we are going to do next. Here's the cubic function. Now, A, B, C, and D here have nothing to do with the A, B, C, and D from before. And unlike before, we are going to be able to explicitly solve for all 4 of those values in terms of the boundary conditions. We're going to need the derivative to do this. Now, t here is going to vary from t0 to t1, so I've changed this a little bit. This is more general, and it's going to give us more control. Also, I'm going to use delta t in place of t1 minus t0 just to shorten things up until the very end. All right, here we go. The initial position is f of t0. That's d. Like, straight up, that's it. D is the initial position, C is the initial velocity. Already, this is way better than using the sinusoidal curve. Now, here's the final position and final velocity in terms of A and B. So this is 2 equations with 2 variables. We're going to solve this. All right, I'll quickly run you through the math here. We're going to re-express that function only in terms of the boundary conditions. We already know what C and D are. We got to get A and B. So we're going to use our final velocity equation here, isolate A, that gives us that, and then substitute that into the final position equation. That's going to give us that. And then if we solve it for B, there we go. We've got B now in terms of the boundary conditions. So again, that was something that we were not able to do with the sinusoidal function. All right, now we're going to substitute that back and solve for A. So there we go. Now we got A in terms of the boundary conditions, and then substitute those into the original cubic function, and bam, there we have it. It may look a little intimidating, but this is very powerful. It allows us to control the initial and final positions and velocities directly over any time interval of our choosing. Here's how we will type this into Desmos. We're going to make use of lists. Now, there's more velocities than times and positions because we will be controlling incoming and outgoing velocities independently. Now, why are we going to use these? Well, it makes the recall of values very convenient. So if I type t bracket 1 into Desmos, it'll return to me the first value in my list of times. Same thing for the position and the velocity list. So we're not going to type in this exact formula into Desmos. We are going to make these substitutions for all the times, positions, and velocities, and that will give us this formula. So F sub CH, I'm just calling that cubic Hermite. That's named after the guy who worked on this. And then you only have one parameter, which is K, and that's the keyframe at which your curve is going to begin, and it will automatically connect to the next one. So you don't have to type this in. There's a link in the description into Desmos for this. So click that, follow along. Okay, so again, there's a link in the description to this Desmos graph. I recommend, if you want to follow along, that you go click that, so you don't have to sit here and manually type all this yourself. But I've got 4 key times, 4 key positions, 6 key velocities. There's the lists that I said we were going to use. And then here is, of course, that beast of a formula that's going to make our lives easier. This is something I haven't discussed yet. That's a piecewise function connecting all of those individual curves. Because again, these are 3 separate curves, and here's what those look like, right? There's the first cubic, there's the second cubic, there's the third cubic, but you do want these stitched together in a single piecewise function. And then there are the points graphed. Again, all you have to use is the title of those lists, and then the actual animated particles. So let's see what this motion right here, what we have. There we go. So that's following our graph. Okay, something worth noting here is these sliders on Desmos, when you animate them, it doesn't matter what you set the range to be. So here I have 0 to 20. That doesn't actually automatically make it last for 20 seconds. If the playback speed is on 1x, it actually plays for 4 seconds. And then if you really want this to be 20 seconds, you got to set that down to 0.2. But, you know, I'm not going to sit here. We're not going to sit here and wait 20 seconds every time I hit that play button. So I'm going to leave it on 1, which is technically 4 seconds, even though I have my T ranging from 0 to 20. So let's play with this. So here's what this looks like. First of all, I can go ahead and change the timer. When this starts, I'm going to leave it at 0 because that makes it clean, but I could move the second point over to 7 if I really wanted to. We can make this 15. Okay, so that moved that. And notice how it didn't change anything else. We have the same positions and we have the same velocities. My positions, let's start all the way up at 10, and then it looks like the way we have this set up, it's actually going to go beyond 10, then come back down to 8, and then it goes down to, let's make it go down to 1, which pushes it into the negatives, and then come back up to 5. All right, so let's play this. Let's see what this gives us. So see, it goes beyond 10, comes back, goes negative. Okay, cool. So that's working. Good. This is where it gets fun, is I can control the outgoing velocity. So let's make the outgoing velocity, here we go, 1.8, and that's going to shoot it up above 12. And then the incoming velocity is -2. So what you'll notice right here is I have it set that the incoming velocity and the outgoing velocity are both -2. They don't have to be the same. You can have discontinuous velocity. So let's go ahead and change that. Let's go ahead and bounce it, right? This is going to look like a bouncy ball now. So there we go. Let's make that 3. It bounces. It's going to come down, and then let's make it bounce down here. We're going to need a negative velocity. Let's shoot that down into the negatives. And let's have it, there we go. That's cubic looking right there. Okay, so what would this look like? Let's see. There we go. There's the bounce. Bounce again. Yeah, okay, cool. So there you go. Play around with this. Have fun. This is how you can control position and velocity using cubic. Now, the limitation of this, you do not have control over acceleration. That you want a 5th degree equation for. So in the next video, I'm going to bump it up from cubic to quintic, and we will have control over positions, velocities, and accelerations. Thank you for sticking around. If you learned something, please like and subscribe.